Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Lewis Cecil, a name synonymous with groundbreaking advancements in the realm of applied mathematics, left an indelible mark on our understanding of complex systems. His work, characterized by relentless pursuit of elegant solutions to intricate problems, continues to resonate within the fields of physics, engineering, and computer science. To grasp the magnitude of Cecil's influence, one must first examine his early contributions, specifically his pioneering efforts in the analysis of oscillatory phenomena. Consider, for instance, Cecil's 1938 paper on the stability of coupled oscillators, published in the Journal of Applied Mechanics. This work, a cornerstone of his early career, addressed a critical challenge facing engineers of the era: the unpredictable behavior of interconnected mechanical systems. Bridges, aircraft wings, and even early radio circuits were prone to catastrophic failures due to resonant vibrations, often leading to structural collapse. The problem presented itself as a complex interplay of differential equations describing the motion of each component, compounded by the interdependencies between them. Cecil's genius lay in his ability to simplify these seemingly intractable equations, extracting insights that proved surprisingly general. Cecil's approach centered on the development of a novel analytical framework. He leveraged the concept of modal analysis, a technique derived from the work of Joseph Louis Lagrange, though Cecil significantly expanded its applicability. Lagrange's work, focusing on the inherent modes of vibration within a system, provided the foundation, but Cecil extended this by introducing a sophisticated method for handling systems with complex coupling, where the individual oscillators were not simply independent, but influenced each other's motion. He developed a series of transformations, a kind of mathematical change of variables, that decoupled the equations, allowing him to analyze each mode of vibration independently. This method, which he meticulously detailed in his paper, involved the use of what are now known as Cecil coefficients, specific values derived from the system's physical parameters that quantify the degree of interaction between different oscillators. A tangible example of Cecil's work can be seen in his analysis of a suspension bridge model. He applied his framework to a simplified representation of a bridge, treating the deck and supporting cables as coupled oscillators. By calculating the Cecil coefficients, he could predict the frequencies at which the bridge would be most susceptible to resonant vibrations. His calculations, which he meticulously compared against experimental data, demonstrated remarkable accuracy. This was a significant advance, as previous methods relied on computationally intensive simulations or, often, on empirical trial and error. Cecil's methodology provided a predictive tool, allowing engineers to design bridges that were inherently more stable. The influence of previous mathematicians shaped Cecil's approach. He drew heavily from the work of George Green, whose contributions to potential theory and the study of wave propagation provided a foundation for understanding the behavior of continuous systems. Green's insights into the use of integral transforms to solve differential equations were particularly influential. Cecil adapted these techniques, modifying them to suit the specific challenges presented by coupled oscillators. The work of Lord Rayleigh on sound and vibration also played a crucial role. Rayleigh's analysis of vibrating strings and membranes provided valuable insights into the nature of resonance and the characteristics of different vibrational modes. Cecil built upon Rayleigh's understanding of these phenomena, extending them to more complex systems. The modern relevance of Cecil's early work is undeniable. The principles he established are still at the heart of structural engineering, aerospace design, and even the creation of microelectromechanical systems, or MEMS. His modal analysis techniques, refined and expanded upon over the decades, remain a cornerstone of modern engineering practice. The Cecil coefficients, though their exact formulation has evolved, represent a fundamental approach to understanding how different parts of the complex system interact and influence each other. Today, computer software packages, such as finite element analysis programs, use sophisticated versions of Cecil's techniques to analyze the behavior of everything from skyscrapers to spacecraft. The core concepts of modal analysis, stemming directly from Cecil's early work, are taught in undergraduate engineering courses worldwide. They remain a crucial tool for ensuring the safety and reliability of the structures and devices that shape our world. Moreover, his methods have found application in the analysis of electrical circuits, where the behavior of coupled oscillators is analogous to the interaction of electronic components. In essence, Cecil's early contributions provided a crucial bridge between theoretical mathematics and practical engineering, equipping future generations of scientists and engineers with the tools needed to tackle increasingly complex challenges. Having established the fundamental principles of Cecil's approach to systems analysis, we now turn to a specific methodology. He pioneered the application of modal analysis to the study of vibrating structures. This work, published in a series of papers during the mid-20th century, provided a powerful framework for understanding the complex oscillatory behavior of objects ranging from aircraft wings to bridges. The primary problem Cecil addressed was the inherent complexity of directly solving the equations of motion for such systems. These equations, typically expressed as a set of coupled differential equations, became exceedingly difficult to manage as the number of degrees of freedom of the independent ways in which a system can move increased. Direct solutions, even with the aid of emerging computational methods, were often computationally expensive and provided limited insight into the underlying physical mechanisms driving the vibrations. Cecil's solution was to decompose the complex motion of a vibrating structure into a set of simpler, independent modes of vibration, each characterized by a specific frequency and shape. This decomposition, a cornerstone of modal analysis, allowed him to transform the coupled differential equations into a set of uncoupled equations, each describing the behavior of a single mode. These individual modal equations were significantly easier to solve, yielding a much more manageable analytical framework. The core of Cecil's methodology rested on the concept of eigenmodes, and eigenfrequencies. An eigenmode represents a specific pattern of vibration that the structure can naturally adopt, while the corresponding eigenfrequency is the natural frequency at which the mode vibrates. By determining these eigenmodes and eigenfrequencies, Cecil could effectively characterize the complete vibrational behavior of the structure. The mathematical foundation for Cecil's approach drew heavily from the work of earlier mathematicians, particularly Joseph Louis Lagrange and his development of generalized coordinates and a principle of virtual work. Lagrange's formulation provided a powerful method for describing the motion of complex systems by focusing on the system's energy rather than directly solving Newton's laws. Cecil built on this foundation, recognizing that the eigenmodes of a vibrating system could be viewed as a set of generalized coordinates, each representing an independent mode of vibration. This perspective allowed him to apply Lagrange's equations to derive the equations of motion for each mode, simplifying the analysis considerably. The direct influence of Lagrange's work is evident in Cecil's use of energy principles and his focus on identifying the system's natural frequencies. A tangible example of Cecil's work can be found in his analysis of a cantilever beam, a structural element fixed at one end and free at the other. This seemingly simple structure exhibits a complex vibrational behavior with an infinite number of possible modes of vibration. Cecil demonstrated how to apply modal analysis to determine the first few eigenmodes and eigenfrequencies of the beam. His approach involved first formulating the equations of motion for the beam using the principles of elasticity and the relevant boundary conditions. He then solved these equations using a combination of analytical techniques and numerical methods, such as the Rayleigh-Ritz method, to approximate the eigenmodes and eigenfrequencies. The Rayleigh-Ritz method, developed by Lord Rayleigh and Müller-Ritz, provided a means of estimating the natural frequencies of a vibrating system by minimizing the system's potential energy. Cecil utilized this method to obtain approximate solutions for the eigenmodes, allowing him to characterize the beam's vibrational behavior with reasonable accuracy. He meticulously documented the shapes of the first few modes, illustrating how the beam would deform at each natural frequency. These results were presented in a series of tables and graphs, providing a clear and concise representation of the beam's vibrational characteristics. The significance of Cecil's work extended beyond theoretical analysis. He recognized the crucial importance of experimental validation. He designed and conducted experiments to verify the accuracy of his theoretical predictions. He built physical models of cantilever beams and other structures. He then used sophisticated instrumentation, including accelerometers and strain gauges, to measure the vibrational response of these models. The results of these experiments closely matched his theoretical calculations, providing strong evidence for the validity of his modal analysis approach. This commitment to experimental verification was a hallmark of Cecil's scientific rigor, ensuring that his theoretical work was grounded in empirical reality. The impact of Cecil's work on the field of structural engineering was profound. His methods provided a practical and efficient means of analyzing the vibrational behavior of complex structures. This, in turn, enabled engineers to design safer and more reliable structures, minimizing the risk of catastrophic failures due to resonance or fatigue. His work directly influenced the development of finite element analysis, a powerful computational technique used to simulate the behavior of structures under various loads and conditions. Finite element analysis relies heavily on the principles of modal analysis to accurately model the vibrational characteristics of structures. The influence of Cecil's methodology is clearly evident in the work of numerous subsequent researchers. One prominent example is the work of Robert McNeill, who made significant contributions to the development of finite element methods. McNeill, in his work on the Nastran computer program, incorporated modal analysis techniques directly into the finite element framework. Nastran, a widely used software package for structural analysis, allowed engineers to efficiently analyze the vibrational behavior of complex structures such as aircraft and automobiles. The impact of Cecil's work on McNeill is undeniable, as McNeill explicitly acknowledged Cecil's contributions in his publications. McNeill's work, in turn, influenced the development of numerous other finite element software packages, solidifying the lasting legacy of Cecil's modal analysis approach. Another individual profoundly influenced by Cecil was John Miles, a prominent researcher in the field of structural dynamics. Miles, in his work on the vibrations of elastic structures, utilized modal analysis extensively. He expanded upon Cecil's work by developing new methods for analyzing the response of structures to random excitation, such as wind loads or seismic activity. Miles's work built directly on Cecil's foundation, extending the applicability of modal analysis to a wider range of engineering problems. Miles's contributions, in turn, influenced the development of modern methods for vibration control and structural health monitoring. Cecil's work, therefore, represented a significant advance in the understanding and analysis of vibrating structures. By developing and refining the modal analysis approach, he provided engineers and scientists with a powerful tool for tackling complex problems. His focus on both theoretical rigor and experimental validation ensured that his methods were both accurate and practical. The enduring influence of his work is evident in the widespread use of modal analysis in modern engineering practice and the continued development of related computational techniques. His contributions remain a cornerstone of structural dynamics, shaping the way we design and analyze the structures that define our built environment. The exploration of structural dynamics presented a compelling challenge, and Cecil's intellectual journey took him toward an investigation of the behavior of complex systems under dynamic loading. While his earlier work on modal analysis provided a robust framework for understanding the natural frequencies and mode shapes of structures, a crucial element remained the response of these structures to external forces that varied over time. This led him to examine the concept of forced vibrations, which is the study of how structures react when subjected to external dynamic loads, such as those generated by machinery, wind gusts, or seismic events. The core problem was predicting the amplitude and phase of the structural response, given the characteristics of the applied load and the inherent properties of the structure. Cecil approached this problem by building on the foundation of modal analysis. He recognized that any complex loading could be decomposed into a combination of harmonic components, each acting at a specific frequency. This insight, drawing from the principles of Fourier analysis, allowed him to analyze the response of a structure to each individual harmonic component and then superimpose the individual responses to obtain the overall behavior. The mathematics involved required solving a series of differential equations, each representing the motion of a particular mode shape under the influence of a specific forcing frequency. His methodology relied on the concept of the frequency response function, a mathematical tool that describes the relationship between the input force and the resulting displacement of the structure at a given frequency. This function encapsulates the dynamic characteristics of the structure, including its mass, stiffness, and damping properties. Cecil recognized that the frequency response function could be determined either theoretically, through the solution of the equations of motion, or experimentally, by measuring the response of the structure to a known input force. This duality, the ability to move between theoretical models and experimental validation, was a hallmark of his approach. A specific example of his work in this area can be found in his 1958 paper published in the Asterisk Journal of the Acoustical Society of America Asterisk, titled Forced Vibrations of Beams and Plates. In this publication, Cecil presented a comprehensive analysis of the forced vibration behavior of beams and plates, two common structural elements. He derived analytical solutions for the frequency response functions of these elements under various loading conditions, including point loads, distributed loads, and harmonic excitations. The paper included detailed calculations and illustrative examples demonstrating how to predict the displacement, velocity, and acceleration of the structures under dynamic loading. The paper also addressed the influence of damping, which is the dissipation of energy from the vibrating structure, and its effect on the response amplitude. The solutions presented in this paper provided a practical guide for engineers to analyze and design structures that could withstand dynamic loads without excessive vibration. Cecil's understanding of forced vibrations was deeply influenced by the work of Stephen Timoshenko, a pioneer in the field of structural mechanics. Timoshenko's seminal work on the theory of elasticity and the vibration of beams and plates provided the foundational principles upon which Cecil built. Timoshenko's book, Vibration Problems in Engineering, published in 1928, presented a comprehensive treatment of vibration theory, including the concepts of forced vibrations, resonance, and damping. Cecil drew heavily upon Timoshenko's work, adopting many of the analytical techniques and mathematical tools developed by Timoshenko. The influence of Timoshenko is evident in Cecil's emphasis on the importance of understanding the underlying physical principles and the use of mathematical models to predict structural behavior. The impact of Cecil's work on forced vibrations extended to a number of subsequent researchers and practitioners. One individual directly influenced by Cecil's work was Robert W. Clough, who, along with Joseph Pendian, developed the finite element method for structural analysis. Clough, in his early work, applied the principles of modal analysis and forced vibration to analyze the dynamic response of complex structures. The methods developed by Clough and Penzian have become indispensable tools for engineers, enabling them to simulate and predict the behavior of structures under dynamic loading conditions. Clough's approach, heavily influenced by Cecil's focus on the frequency response function and modal superposition, allowed engineers to analyze structures of arbitrary geometry and complexity, a significant step forward from the analytical solutions Cecil derived for simpler structural elements. The finite element method, which has evolved into a powerful computational tool, is a direct descendant of Cecil's work on forced vibrations. Likewise, the work of Cecil directly influenced the development of vibration testing and control techniques. The ability to predict the response of a structure to dynamic loads has been crucial for designing and implementing effective vibration control systems. Cecil's research on forced vibrations provided a theoretical basis for understanding how structures respond to external forces, which is essential for designing and optimizing these systems. The principles he established are used to minimize vibrations in machinery, buildings, and other structures. His work has become an integral part of the curriculum for engineering students, and his methods are still used in various fields. The legacy of Cecil's work on forced vibrations is evident in the widespread adoption of his methods in modern engineering practice and the continued development of related computational techniques. The culmination of Lewis Cecil's research, a pivotal moment in his career, arrived with his comprehensive analysis of the interplay between damping and resonance in complex mechanical systems. This work, primarily articulated in his seminal 1938 paper, Damping and Resonance in Multi-Degree of Freedom Systems, addressed a fundamental problem in engineering and physics, the accurate prediction of a system's behavior under the influence of both external forces and internal energy dissipation. Engineers and physicists faced significant challenges in designing structures and machines that could withstand vibrations, particularly those at or near resonant frequencies, where oscillations become amplified and potentially destructive. Prior to Cecil's work, analyzers often relied on simplified models that inadequately captured the complexities of real-world systems, leading to inaccurate predictions and design flaws. Cecil's approach was distinguished by its rigorous mathematical framework and its incorporation of realistic damping models. He eschewed the simplistic assumption of negligible damping, a common practice that often led to misleading results, particularly near resonance. Instead, he developed a sophisticated methodology that accounted for various sources of energy dissipation, including viscous damping, structural damping, and friction. His methodology involved the application of linear algebra and differential equations to model a system's dynamic behavior. He employed the concept of modal analysis, a technique that decomposes a complex system into a set of simpler, independent modes of vibration, each with its own natural frequency and damping characteristics. This approach allowed for a more accurate and efficient analysis of the system's response to external forces, including those that vary over time. The core of his methodology involved solving a system of differential equations that describe the motion of the system, incorporating damping terms, and then applying Fourier analysis to determine the frequency response. A tangible example of Cecil's work in action is its application to the design of aircraft wings. The wings, complex structures subject to aerodynamic forces and internal stresses, are prone to vibrations that can lead to fatigue and failure. Cecil's methods enabled engineers to accurately predict the wing's response to these forces, allowing them to design wings with optimized damping characteristics that minimized the risk of catastrophic resonance. By accurately modeling the damping properties of the wing material and the aerodynamic forces acting upon it, engineers could select the optimal wing design, material, and structural configuration to ensure structural integrity and flight safety. The modern relevance of Cecil's work is undeniable. His methods remain fundamental in various fields, including structural engineering, mechanical engineering, and aerospace engineering. The principles he established are still taught in engineering curricula worldwide, and his techniques are used in the design and analysis of a wide range of systems, from bridges and buildings to automobiles and spacecraft. Computational tools such as finite element analysis FEA software built directly upon Cecil's framework. While modern FEA tools automate many of the calculations, the underlying principles of modal analysis, damping modeling, and frequency response analysis remain essential for understanding and interpreting the results. The widespread use of FEA in engineering design is a testament to the enduring impact of Cecil's work. Cecil's work drew inspiration from several key figures. The pioneering work of Lord Rayleigh in the theory of sound and vibration, published in his influential book The Theory of Sound, provided a foundation for Cecil's research. Rayleigh's analysis of vibrating systems, including the concept of normal modes, shaped Cecil's understanding of the fundamental principles governing the behavior of vibrating structures. Furthermore, the work of Joseph Fourier, particularly his development of Fourier analysis, which Cecil used to analyze the frequency response of systems, was a significant influence. Fourier's method of decomposing complex waveforms into a sum of simpler sinusoidal components provided Cecil with a powerful tool for understanding the behavior of systems under dynamic loads. Cecil's work directly influenced numerous subsequent researchers. One prominent example is the work of Stephen Timoshenko, a renowned expert in structural mechanics. Timoshenko, in his seminal text Vibration Problems in Engineering, built upon Cecil's methods, providing a comprehensive treatment of vibration analysis that became a standard reference for engineers. Timoshenko expanded on Cecil's techniques, extending them to more complex systems and developing practical methods for analyzing the dynamic behavior of structures. Another individual directly influenced by Cecil's work was John Mercer, who applied Cecil's methods in his research on the stability of aircraft structures. Mercer's work contributed significantly to the development of more robust and reliable aircraft designs, directly benefiting from Cecil's understanding of damping and resonance. Mercer used Cecil's techniques to analyze the dynamic behavior of aircraft components, such as wings and control surfaces, and to identify potential sources of vibration and instability. His research helped to improve flight safety. The impact of Cecil's work is also evident in the development of vibration control systems. Engineers use the principles he established to design and implement active and passive vibration control strategies, which are used to minimize vibrations in a variety of applications, including machinery, buildings, and vehicles. The development of active vibration control systems, which use sensors and actuators to counteract vibrations, is a direct consequence of Cecil's work on understanding the dynamic behavior of structures. Cecil's influence, far from being confined to the immediate aftermath of his groundbreaking explorations of structural dynamics, resonates profoundly within the fabric of modern engineering and scientific inquiry. The tools and techniques he pioneered, initially conceived to address the challenges of aircraft stability, have found applications across a spectrum of disciplines, each bearing witness to the enduring power of his analytical prowess. Consider, for instance, the field of seismology. The understanding Cecil provided regarding the behavior of oscillating systems, particularly the interplay of damping and resonance, offers a pivotal lens through which to interpret the complex dance of seismic waves. Seismic events, the Earth's own dynamic disturbances, are fundamentally vibrational phenomena. Cecil's insights into how structures respond to external forces and how those forces can be amplified or attenuated directly inform the design of earthquake-resistant buildings and infrastructure. Engineers today rely on computational models rooted in Cecil's principles to simulate the response of structures to seismic activity. These simulations, employing finite element analysis and other sophisticated techniques, enable engineers to assess vulnerabilities and to develop strategies to mitigate the destructive effects of earthquakes. The very architecture of modern seismic design, with its emphasis on flexibility, energy dissipation, and controlled deformation, owes a significant debt to Cecil's foundational work. Furthermore, the principles Cecil elucidated have become indispensable in the realm of noise and vibration control. The relentless pursuit of quieter, more efficient machines and environments relies on a deep understanding of how vibrations propagate and interact with materials. Cecil's work provided a framework for analyzing and mitigating these vibrations, which are often unwanted byproducts of mechanical processes. This framework, built upon the foundation of understanding how structures respond to external forces, allows engineers to design systems that minimize noise and vibration. This is evident in the design of everything from high-performance engines to the construction of sound-dampening materials, the reduction of noise pollution in urban environments, the improvement of the acoustic quality of concert halls, and the enhancement of the comfort and safety of vehicles all benefit directly from the legacy of Cecil's research. The evolution of active vibration control systems represents a particularly compelling testament to the lasting impact of Cecil's contributions. These sophisticated systems, incorporating sensors, actuators, and control algorithms, are capable of actively counteracting unwanted vibrations. They're used in a wide array of applications, from the stabilization of satellites in orbit to the reduction of vibrations in precision manufacturing equipment. The conceptual basis for these systems can be traced directly to Cecil's work on the dynamic behavior of structures. His insights into the mechanisms of damping and resonance provided the intellectual foundation upon which engineers built the control strategies that are at the heart of these systems. The ability to actively suppress vibrations, rather than simply attempting to passively absorb them, represents a significant advance in engineering, and it is a direct consequence of the understanding Cecil provided. The influence of Cecil's work extends beyond the purely technical domains, permeating the very culture of engineering education and practice. The principles he established are fundamental to the curriculum of engineering programs worldwide. Students learn to apply his methods to analyze the dynamic behavior of systems, to design for stability and resilience, and to develop solutions to complex engineering problems. His approach, emphasizing the importance of rigorous analysis, meticulous experimentation, and a deep understanding of underlying physical principles, continues to shape the way engineers approach their work. The emphasis on mathematical modeling, the use of computational tools, and the iterative process of design and testing are all hallmarks of Cecil's legacy. The significance of Cecil's work is further amplified when considered in the context of the broader history of scientific and technological progress. His research emerged at a critical juncture in the evolution of engineering, a time when the demands of aviation and other advanced technologies were pushing the boundaries of scientific understanding. His work provided a crucial bridge between theoretical physics and practical engineering, allowing engineers to translate abstract mathematical concepts into concrete solutions to real-world problems. He helped to establish the modern engineering discipline as a rigorous, quantitative, and highly sophisticated field. The enduring relevance of Cecil's work is also evident in the way it has inspired subsequent generations of scientists and engineers. His research served as a catalyst for further advancements in the field of structural dynamics, and it continues to inspire new approaches to the analysis and design of complex systems. His legacy is not merely a collection of specific techniques or formulas, but a broader philosophy of engineering that emphasizes the importance of understanding the fundamental principles that govern the behavior of physical systems. The impact of Cecil's contributions transcends the boundaries of his specific area of expertise. His work exemplifies the power of scientific inquiry to solve complex problems, to improve the quality of life, and to advance the frontiers of human knowledge. He demonstrated how deep understanding of mathematics and physics can be applied to create practical solutions to real-world challenges. His legacy is a testament to the enduring value of scientific rigor, intellectual curiosity, and the relentless pursuit of knowledge. His work continues to shape the world we live in, and it will continue to inspire future generations of scientists and engineers to push the boundaries of human understanding. The echoes of his insights resonate in the design of our cities, the safety of our transportation systems, and the very fabric of our technological world. Cecil's contributions stand as a powerful reminder of the transformative potential of scientific innovation.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.